Okay guys, welcome to the video. In this video we're going to be going through the modernization of the RPAC bindings for C++. RPAC is a sparse linear algebra library, so it's to solve eigenvalues and eigenvectors of sparse matrices, both real and complex. And what we want to do is modernize the interfaces for the package, and these include what's inside this function here, so what's inside this header file, essentially the function names that we need to call in order to access the library, and these match up with the corresponding names for the package, which is written in FORTRAN 77, so quite old, but there's still some C bindings here. We can use those from C++. Type here is encoded inside the front of the function, so this is typical FORTRAN style. We have the type at the front, so S would be single precision floating point, and we can see that matches up with the float specifiers here in the types. And then if we look to double as well, we see D for double precision, we see pointers to double. And if we go down and look at the complex, we have C for complex single precision, so we see float complex, and again the same for Z. That's double precision complex. So if we go back to the C++ bindings, what these are is essentially the same apart from extern C. So this extern C means that this function will be mangled. But what we want to do is remove this need. We're specifying the type twice. We're specifying it inside the function name through the S, and again through the type that we have to put in. What we can do is just have one function called saupd underscore C and have that overloaded for the specific types that we need to do. In this way, we reduce the number of functions, or the function names rather, and it becomes a little bit clearer, a bit easier to understand. We can see how these bindings here are used through the test example inside the RPAC package. We have 4 functions in total. So we have 2 functions which do the actual meat of the work, and that's functions SS for the real eigenvalue solver, and we have CN for the complex one. Now these function names aren't particularly descriptive, so if you were to write this C++ using modern standards or modern best practices, it would look a lot different. And so what we're going to do is go through and modernize this test routine so people coming in can see best practices. We can also make this easier to read. Instead of just this big blob here of all of this code, we can actually pull this out into something that's a little bit easier to read and understand. And also go through and change all these C style programming. And we can see quite simply, if we look at the C test example, these are essentially the same. We've got a type change here, so instead of S we have D for double, and then we have the same glob of code here. All that's changed really is new now instead of malloc, and I guess the matching delete down here somewhere, so delete instead of free. And what we're going to do is just have the C++ standard library handle this all for us through its std vector class as well as std array, and we'll see where those plan on getting used in a moment. So we'll just ignore the complex example for the moment. We'll focus on just the real one. We start off with just this, again, line after line of code. There's no separation of ideas here, so it's very confusing for someone to see what's going on and understand it. However, we do have some good practice here. We've got initialization of a variable, so in this case the variable iDo is initialized to 0, so there's no chance of iDo being uninitialized. We know that's set to 0, so that's really good practice. We always want to initialize our variables when we create them, so we don't have any sort of uninitialized memory, which should just be garbage or something worse. You can also see here, strangely enough, that in front of this new there's actually a C style cast to a float pointer. We don't need this. The new already returns the correct type pointer So this is one of the benefits, I guess, of using C++. And we can just probe this a little bit further. We have a C-style array declaration here. So this is creating n floats on the stack. So we're not doing dynamic memory allocation here. It's just static memory allocation of 1000 here. Okay, and then we look down at where we do our dynamic allocation, and we see here that we have number of eigenvalues plus 1. So this is 10. So number of eigenvalues is here, and for some reason we're dynamically allocating 10 values onto the heap, and 1000 on the stack. This is very confusing. I'm not exactly sure why this was done, but we can go through and just change this to use best practices. Okay, so now we can use the interface, the bindings here. So you can see here that we specify the type, as well as the type indirectly through these pointers here. And then we call this smat vector of some pointer arithmetic here. I guess we get the offset, and we take the address of this offset, which matches with the pointer parameters that we see here. And then of course some more C-style loop indices here. We print out values to the terminal, and then we also check to make sure that the values are correct. So we check that the absolute value of this eigenvalue is as we would expect, which just should be from 1 to 1000. And then we return from the function. So if everything goes well, we return 0 down here. So there are a few problems with this test code. It runs correctly, however I think it's the only current example of using C++ inside RPAC. I think we can do a little bit better in terms of showing best practices, as well as making the code a lot clearer and easier to understand. For example, we could just start at the top here. We've got this include rpac.hpp. Usually you want the bindings to occur at the top. So in case you do any sort of forward declarations or something like this, and you have the implementation under it, you don't get the types around the wrong way. So you always have whatever you're doing and then your concrete types underneath. So forward declarations first. Here we also have, I guess we start at the top. We've got iStream, this is fine. We've got C math, this is including C standard library, math library. This is okay. And then we've also got this string. This is for our parameters here. And then we have this complex.h, and this complex.h is from the C library. It's not C++. It will work, however, because C is a subset of C++, but we want to actually use the proper C++ types here to get all the benefits that we get with using C++ for this kind of stuff. All right, and then we just do some type definitions here. Now, one of the biggest problems with just passing these pointers in, there's no ownership semantics, or we're just passing some pointer into memory, and it's not exactly clear what this means just by looking at the signatures. We have some couple of floats. We don't know if one's being written to or one's not. If they alias, which means perhaps X points to some position behind Y, we don't know. So what the compiler has to do is generate some fairly suboptimal code for this, unless it can prove that these two types here don't alias. And what we can do is, for high performance applications, this restrict keyword here would be important, but this is not. This is just a test, so we just make this more clear what we're actually doing. You can read this here. So this is using what they call east const. Basically, we put the const specifier on the right hand side because the compiler reads it such that the const specifier applies to what's on the left. If there's nothing on the left, it applies to what's on the right. So we can use that here. We have a const pointer. So we have a pointer to somewhere in memory, and it's always going to point to that place in memory because we have this const here. And then we have another const specifier, and that applies to the float. So again, right to left. So we have a const pointer, which points to something which is const. So that means the pointer can't change where it goes, and the values which the pointer points to also can't change. Now we could also do the same here for y, which means we could put const here, and this means that the pointer won't change, but the values that we're specifying, or the values that we're pointing to, will. And we can see from this loop, this is clear. So yi is being mutated, and x of I is just being read. So again, we have the same C style for loop here. We can do this in line. It's always good to have the correct braces around so it's all very clear, explicit. And here we also have a C style cast. We want to change this integer value into a floating point number. In fact, what we should be using is static cast here. So this is very clear that we're statically casting this integer, I plus 1 in this case, into a float, and then multiplying it by this. Okay, so we can apply this kind of organization, these techniques here to this code, and we can change it from being a C-style example into C++. We're kind of using best practices and making things a little bit more robust, of course. We've got the plan here. We'll have to go through and change the C style call. So for example, fabs, this is the floating point absolute value. We can just use the standard library implementation in C++, and that's stood abs, absolute, and that's overloaded for floating point types. So we don't need a special function signature for that, special function name rather. And again, we see more C-style conversions here, or casts. We should be using the specified or the provided one, static cast. And that's roughly about it. We'll get started on this work shortly. And again, you can see the same. Just a quick look at how the complex is handled. It's exactly the same, apart from small changes to the type. So instead of having a float, we now have a complex. And again, we have the same pattern. Of course, this is basically copy and paste with type changes and function changes. First of all, changing these bindings. So we'll leave this example alone, so we know this works for now, and we can go through and test with it. Then we'll change these bindings here. So this involves doing conversions between the double complex here and the std complex, templated over a double type. And this is guaranteed from C++11 to have the same binary layout, which means we can tell the compiler, just interpret these set of binary data in terms of a double complex. They are always ordered, or they're guaranteed to be ordered, real, imaginary, where they occur one after another in memory. So this is good. We can use this to maintain compatibilities with C in order to convert C++ bindings to call the C ones under the hood. And this should give us a nice win, a little bit less work on the programmer side, which is what we're always striving for, as well as maintaining the efficiency and the static type checking that we like. So that concludes this video. The next video will be about performing these actual changes, and we can go through how we're going to convert all of this stuff and make sure it works. Okay, so if you like this video, hit the subscribe button for more of them. If you have any ideas on what can change or what would be good, then post those in the comments below, and we'll see you in the next video.